Okay, hi guys, so we'll be continuing on seeing more examples on the geometrical and optical isomerism of octahedral complexes. So let's say we have Ma3B2C. So if we draw the structure of the same, then let's say we are first drawing the cis structure. So these three A are in cis, these two B's, and C is placed here. So is this optically active or inactive? That's the question. So if we look at this compound and we have a slightly tilted plane cutting the atoms C, M and A into two halves. So as a result, this axial A atom and this equatorial A atom would be mirror images of each other, and similarly this equatorial B atom and this axial lower B atom would be mirror images of each other. I want to imagine this plane that it is coming. This is the equatorial plane, this is the axial plane, this is just cutting it at 45-degree angle. Okay, so this in the z-axis. Okay, so as a result you can easily see that in the axial plane and the equatorial plane, as it is cutting 45-degree from both the axes, so these two would be mirror images, and in the same way it is going down also with a tilted angle, and it would be again 45 and 45-degree with the axial and the equatorial plane. So it is optically inactive because we are having a plane of symmetry. Okay, so if we draw the trans of this, then first let us draw the trans with respect to all ligands. So A and A are in trans, we have positioned it here. B and B are also in trans, and A and C, the remaining pair, is also in trans. Okay, this would be optically inactive. Why? Because we can have a equatorial plane cutting all these atoms C, B, A and B into two halves, and also the upper axial and the lower axial A ligand will have or rather are forming a mirror image with respect to each other. Okay, next let us draw the trans with respect to only A and BC. So only A and BC, these two B are in cis positions with respect to each other. So again we can have a equatorial plane of symmetry. So again it is achiral compound or it is optically inactive. So the total number of geometrical isomers in this case would be 3, 1 cis and 2 trans. Okay, and total number of stereoisomers would also be the same. Why is this the case? Because we are not having any optically active compound. Okay, next let us see this compound, which is, let me write it here, M double A whole thrice N plus. So we have M double A whole thrice plus minus N. Okay, so if you draw the D form of the same, so it would be something like this. These two bidentate donating sides, or rather these two donating sides of a bidentate ligand are connected to each other. Similarly these two and these two. So if we look into it, this A is coming towards your face, this A is going away from your face, and these two are connected. This A is going away from your face or into the screen, and this A is on the plus Z axis or the axial upper axial position. This A is coming towards you or coming out of the screen or coming out of the page, and this A is down the Z axis or down the axial plane. So these two are connected. Okay, so if we draw the mirror image of it, we'll be getting something like this, in which this axial A atom is bonded with this A atom, which is, this A atom is again going inside the plane or away from you. This A atom is coming into you or out of the screen, and it is getting bonded with the A atom, or rather the A donating or coordinating side, which is in the minus Z axis. Similarly these two A's are also connected. Okay, so we want to check that whether these two are superimposable or not. So let's rotate it upside down with 180 degree, so that we get something like this structure. That, or rather, we can also have it moved in the equatorial plane with 180 degree rotation, such that these two atoms are hit in this position and are connected to each other. So if we do that, then what will we be getting? We'll be getting something like this structure, that we have M atom here, we are rotating this 180 degree anti-clockwise. Okay, so what will we be getting? This A atom would come here, this A atom would come here, these two would be getting bonded. Okay, and what would be the case here? For this A atom, it would be going inside the plane in the equatorial axis or in the equatorial plane, and would be bonded with the axial A atom. So I'm just showing the dash here to denote that it is, this bond is going from inside the plane to towards Z plane, and similarly these two atoms would be also bonded. So can we say that these two are superimposable? No. Why? Because this axial atom and this equatorial atom should not be bonded in the original case had they been superimposable, as this A atom and this A atom are bonded, but this is not the case in this complex compound. Hence these two are not superimposable, and these two are optically active compounds. Okay, so total stereoisomers here would be just 2. Okay, and there will be no geometrical isomerism in this case. Okay, we have seen this already in our previous lectures, that in octahedral complexes we have seen several examples which will not show geometrical isomerism. Let's see this compound. So again, this has 2 A's and B2 connected here. So again, this would be optically active compound. Okay, and why is this the case? This is the cis form. Let's say it is D, and this would be cis form L. This would be optically active. Why? Because if we draw the mirror image of it, it would be A here, A here, A here, A here, and BB here. So if we again rotate it with 180 degree anti-clockwise, what will we be getting? We'll be getting that this A would be coming at the position of B in the newly formed rotated complex compound. So we would be having this A here, and this A is actually bonded with the lower axial A atom. So it would be bonded here, and this A would be coming towards your face, as originally it was going into the plane. So now it would be coming after rotation. After rotation, it would be coming towards your face, and this would be bonded with the axial A atom. So are these two complexes superimposable? No. Hence these two are mirror images of each other and are optically active. Okay, and similarly, if we see the transform of the same, transform would be something like this: A here, A here, B, B, A, A. So again, these two are connected. So now we can have a plane of symmetry. Okay, cutting all these 4 atoms and the central metal atom. Hence there would be a POC, as these two B's would be mirror images of each other. Okay, so this would be the plane. Okay, and these two B's would be mirror images of each other. So there would be only one trans which would be optically inactive. So total number of geometrical isomers here would be 3, or rather 2, 1 cis and 1 trans, and total stereoisomers here would be 3, because the 1 cis geometrical isomer is also optically active. Stereoisomer. So that number would be 3. Okay, so with this we come to the end of this lecture. We'll meet in the next lecture. So till then, good luck and goodbye.